Welcome to the Crazy Hat Chemist. So here's another video on bonding. So let's get moving. Bam! So today we're talking about the valence bond theory. The valence bond theory was designed by Linus Pauling, and he actually had two unshared Nobel Prizes. One in chemistry and one in peace. Okay, so valence bond theory is based on this concept of valence shell electron pair repulsion, which we call VSEPR. So we're going to be using VSEPR a lot. Okay, VSEPR gives a three-dimensional shape of a molecule or an ion, okay, based on the electrons repulsing each other. Electrons are of the same charge and they want to move away from each other, from their other adjacent atoms as much as possible, so you'll get the three-dimensional shape based on this electron pair repulsion. So they want to diminish the repulsion in between these. VSEPR leads to a molecular shape, molecular geometry for that molecule or ion, and I'm going to use an axe for this shape. So let's figure out what that axe actually means here. Okay, there is an axe for you just so that you can remind yourself of what an axe looks like. Okay, and the A in the axe is for the central element. Okay, the X on the axe is for the elements that surround the central element. And the E for the axe are lone pairs of electrons only on the A, that's the central element. If there are lone pairs of electrons on the outside elements, those are the X's, we don't care for our VSEPR shape. It doesn't matter for the shape itself. Okay, so let's give you a pictorial diagram of what this might look like. Okay, so our central element is A. Okay, and then we're going to have an X marks the spot pattern where we place our electrons and our other elements. We've done this for a variety of the Lewis dot structures already previously. So we're going to place some X's around here. The X's are representing elements. This would be a tetrahedral structure because these X's are at the corners of a tetrahedron. Okay, now if I take away one of these X's and replace it with an E, that would be a lone pair of electrons on the A, that is the central element. This will give me a trigonal pyramidal structure. I can actually do the same thing and remove another element that's attached to the central element and replace it with a lone pair of electrons. This will give me a bent or angular shape. Okay, now these are elements of A that follow the octet rule. Now we do know that there are elements that are in period 3 or greater that can exceed the octet rule and be hypervalent. And so here's an example of that. A is the central element again. Now instead of having 4 region potential outside this, we can have a potential of 6. We're going to actually have 2 groupings of this. There's going to be a grouping of 5 and a grouping of 6. The grouping of 5 is a trigonal bipyramidal structure. The grouping of 6 is an octahedral structure. Octahedral, of course, is how many? 8, like an octopus. So octahedral, you think, I only have, look at this, how many X's and how many elements around A? Only 6. But those 6 elements are at the apexes or corners, okay, to this octahedral structure, which will give me 8 faces. That's why it's octahedral in shape. So what we're going to do is we're going to remove one of the X's and then we're going to replace it with an E, and that's a lone pair of electrons here. We can do this yet again, remove an X, and that's an element, and replace it with an E. We can remove an X, an element, and replace it with an E. Remember, the E's are lone pairs of electrons. The X's are atoms that are surrounding that A, that central element. Okay, this would actually give us a linear type structure with that octahedral base. Okay, and right over here is our AXE pattern. The A, there's only going to be a single A. Okay, so we're really good with that. It's really nice and easy. The X, we're going to count up how many X's are around the central element. Okay, and then that would give us a lead into what this structure is. Then we're going to count up the number of E's around that central element, and between the A, the X, and the E, the number of X's, the number of E's around that central element, we will be able to determine the three-dimensional shape name. That is the molecular geometry using the valence bond theory and VSEPR. Hopefully you enjoyed that, and I got an appropriate hat for this, of course, because it's an octopus. And like an octahedron, an octopus has 8 legs, like an octahedron has 8 sides. Give me a thumbs up if you like that video. Give me a thumbs up if you like the octopus hat. And subscribe to my YouTube channel, and I'll see you next time. Bye now.